Everyone. My name is Prudence Mhlophe, and I'm going to talk about the use of biochar for salt-affected soils. I'm going to talk about the possible role of spent coffee grounds-derived biochar. This will be a mechanistic basis for the use of spent coffee grounds biochar. I'm a PhD student who's currently working on the use of spent coffee grounds biochar for the remediation of heavy metals in urban soils. So I've created some biochar, and based on the characteristics of this biochar, I'm going to talk about what role it could play in the remediation of salt-affected soils. So my presentation, I'm going to talk about what salt-affected soils are, what the problem with soil-affected soils is, how biochar works, and then lastly, I'm going to talk about the biochar that I've produced and how the characteristics that I've got from this biochar can be applied for the remediation of salt-affected soils. So the problem with salt-affected soils is that over 1,381 million hectares of land is salt-affected worldwide. That's from FAO from 2024. So salt-affected soils is an umbrella term for three distinct soil conditions. Saline soils, these have excess soluble salts, which is measured by electrical conductivity. Can you still see my screen?
Yes, ma'am.
Sorry, I wasn't seeing the screen. Okay, and then sodic soils, these are soils that have excess exchangeable sodium. This is measured by the sodium adsorption ratio on the exchangeable sodium percentage. And then saline sodic, these have got both conditions, and these are the hardest to diagnose and remediate. So why this matters? Salt affects land and its ability to produce food. So salinity causes osmotic stress, ion toxicity, and nutrient balance. And then sodicity, on the other hand, causes the clay aggregates to break apart, and then the soil structure collapses. Still, that affects its ability to produce food and any other soil uses that you need. And with the low conductivity, because of the sodicity, water and air cannot move. So the usual remediation methods for salt-affected soil, first it's gypsum and amendments. This uses calcium, which is meant to displace sodium, but this requires large amounts and multiple doses. So for low-income countries, this is very expensive and it's not always practical. And then the leaching regimes where they use water to leach out all the salts and the sodium, but this requires a lot of water, and most arid and semi-arid regions that is already a limitation. So the limitations to these two conventional remediation methods is what necessitates the need for a low cost and multifunctional amendment. So this is where biochar comes in. So biochar is a charcoal-like substance produced from burning biomass in the absence of oxygen. So how does biochar work in remediation of salt-affected soils? So first of all, biochar is very porous and has a large surface area. So with this large surface area, biochar absorbs the sodium, removing it from the salts and so reducing the sodicity or the salinity of the soil. It's also the particle size and bulk density of biochar. This, while it's an advantage, it can also be a limitation, because if the particles are too small, they can clog the soil pores, causing a compaction and affecting the movement of water. However, so the biochar, because of its porosity, can improve the water holding capacity. As you can see in the illustration there, it can enable the leaching of excess salts, and especially in areas, arid and semi-arid areas, this is important. An improved water holding capacity of a soil means that you can produce more from that soil. So the cation exchange capacity of the biochar, how that is effective in remediation of salt-affected soils, is that the exchanges, the other salts replace sodium in the soil, reducing that sodium and the effects that we mentioned earlier. Also, biochar is usually alkaline, and so that alkalinity acts as it has a liming effect, especially for acidic and saline soils that have low pH. So when you add the alkaline biochar, that improves the pH and it improves the growth conditions for soils. So ash content and mineral composition. The ash content of biochar contains minerals such as calcium, magnesium, potassium. And so that not only adds to the fertility of the soil, but it also helps the soil. So the electrical conductivity, this is very critical. I'll come back to it when I'm talking about the SCG, the spent coffee ground biochar, because that can be high. So the electrical, when you're selecting a biochar for the use in salt affected soil, you have to be very careful, because the high soils, the biochar that is high electrical conductivity will include soluble salts, may make salinity even worse than before. So that is one function that has to be looked at carefully when selecting a biochar. And then the surface functional groups. So the surface functional groups, these are very critical. This is a very critical part of biochar, because these surface functional groups are the ones that can bond with reduce the exchangeable sodium. The same effect that I talked about in the remediation of heavy metals. They improve water and nutrient use, and they can promote plant growth in saline soils. So the good thing about biochar as well is that the properties of biochar are tunable. So you can select biochar you can design biochar for the soil that you have. So if you know that you've got an acidic soil, you can design biochar that is you select feedstocks that produces biochar with higher pH. That way you know that it is going to work. So when you're looking at salt affected soils, you want biochar that is low sodium, low inherent sodium and chlorine, high cellulose relative to lignin, and preferably low potassium. Pyrolysis temperature, you can also manage this. So low temperature biochars have got higher cation exchange capacity. They've got higher exchange capacity, and they also have higher surface area as well, and they've got lower ash, and pH is average, while higher temperature biochars have got reduced cation exchange capacity but greater surface area and porosity, and also stable carbon, but they do tend to have fewer oxygen containing functional groups, as we mentioned earlier that the functional groups are important for the reduction of salinity. So pyrolysis conditions as well, you can change this by changing the temperature and the conditions as well. So you can change the inert gas, which can reduce the oxidation that will result in the surface salts that increase that contribute to the salinity of the soil. So particle and application design. So particle size, you can decide, you can either apply this biochar as a powder, or you can apply it as pellets, that depending on the type of the soil that you have. And then the chemical modification, you can actually add calcium directly to the biochar before application, so that it displaces the sodium, especially when you're dealing with sodic soils. And with structural engineering, you can also use activation such as steam to improve the pore structures and surface area. And so you can engineer it specifically for the soil that you are working with. So now, spent coffee grounds. Spent coffee grounds are abundant, distinctive, but underexplored. Over almost 18 million metric tons of spent coffee grounds are produced this year. And for every kilogram of roasted coffee beans, 600 grams is wasted. So that comes out as waste. So your 60% of your coffee bean is thrown away, and that usually goes into landfill. And when it is in landfill, it creates its own problems. And coffee grounds, spent coffee grounds, are a nitrogen rich product. They've got a very well developed porosity. They've got a modifiable surface chemistry, which I will show in a minute. And also, we've been talking about circular economy. Instead of taking those spent coffee grounds and putting them in the bin or putting them in the landfill, we use them to resolve other problems such as heavy metals and, in this instance, salt affected soils. So the properties of coffee grounds. So the spent coffee grounds that I used were paralyzed at 550. So these are some of the properties. The ones that I've highlighted in red are the ones that we need to be careful about. These would be a challenge in salt affected soils. High potassium is not very good because it will add to the salt level of the soil. They've got lower cation exchange capacity. You'd want a biochar that has a slightly higher cation exchange capacity, and the electrical conductivity of this particular biochar is quite high as well. So you have to worry about particularly the high potassium in spent coffee grounds, and the electrical conductivity may be an issue when you're looking to use it for salt affected soils. But like I said earlier, biochar can be engineered so you can change a few things or add other things. So this is just an illustration of some of the mechanisms of the spent coffee grounds. Outside of the resolving the salt solution, they contain some nitrogen. They contain higher nitrogen than most of the other plant-derived biochar, residue biochars. So it's very good for increasing soil porosity, better aggregation. It can improve infiltration, and it can also, biochar can act as an enhanced microbial habitat in soils. So in my instance, I did modify the biochar. So looking at that, so some of the challenges that I've explained, that the high electrical conductivity can be a problem because it will increase some of the salts, and also we know that spent coffee grounds contain some phenolic compounds that can be toxic to microbes in the soil, so that can be a limitation. And usually for salt affected areas, we do require biochars that have a lower C to N ratio. So some of the applications of if you look at the surface area, so this is the modification with hydrogen peroxide, which is a benign, safe and cheap product to modify the coffee grounds with. As you can see, the improvement in surface area. We are here, just ignore the green and the light blue graphs there, because that was for the raw coffee grounds, not the biochar. So the last two, which is the red and the orange, as you can see, modification with hydrogen peroxide increases both the pore surface area, pore volume, and the overall surface area. And also, if we look at the changes due to the modification as well, when you pyrolyze the raw coffee grounds, you lose a lot of the functional groups, but the oxidation restores some of the functional groups. As you look at that, the change from the red to the orange on here. So the post pyrolysis oxidation improves the biochar. And then this is just a same illustration of the increase in the improvement from the raw biochar when you oxidize it before you use it. And look, this is the SEM images. As you can see, that the porosity is illustrated on there. This is the one on the left is the pristine biochar, and that one is the oxidized biochar. So in conclusion, spent coffee grounds are available and they are low cost. And if you're going to amend them with hydrogen peroxide, which is environmentally benign, they are worth exploring. So biochar is multifunctional. If you've ever studied biochar, you know that it can be used in a lot of other things. And also the SCG Biochar, it works into the sustainability and the circular economy principles. And modifying it with a benign substance like hydrogen peroxide, you improve without creating more waste. And so it is something that's worth exploring. Thank you very much.